Hello, welcome back. In this segment, I want to talk about Diophantine equation, in particular, linear Diophantine equation. For example, if you want to solve a linear equation like 21x plus 15y equal to 12, you want to find integer values for x and y that will satisfy this equation. Okay, such equations were studied by ancient Greeks. For example, Diophantine has studied a lot of these forms of equations, and it's quite interesting that those equations play a critical role in cryptography. I'm going to talk about linear congruences later, but for now, let's talk about solving linear Diophantine equations like this. You are given 21x plus 15y equal to 12. Your goal is to find x and y that satisfy this property. Okay. How do we find the x and y? Let's first run it, and I'll show you something quickly. Okay. So you get x to be minus 8, y to be 12. Okay, you can trust me. I checked the assertion that x is equal to minus 8, y equal to 12 satisfies this equation. That's not the only solution. You can have more than one solution. And I'm going to talk about when we can expect more than one solution. And there are cases where we will not have any solution. For example, if I quickly change this to say 28x and 35y, right, is equal to 60. I'm going to change the code. I changed the comments, which doesn't help. Okay, let's see. For this, we will not have solution. Okay, we can check it. Well, this assertion won't even execute because x and y will not be returned. We can actually print. Let me change it because we are returning a let's see, if solutions is equal to none, that means no solution, right? Then print no solution. Okay. Else we go ahead and print the x and y and check the assertion. Okay. This way we can use the same. Okay, now I need to get the x and y from the solutions. X is the d is the first. I'll explain what d means in a moment, but don't worry about it. X is solutions of 1, y is solutions of 2, meaning these are the values of x. These are the values. Excuse me. When you place it on this equation, we satisfy the right-hand side. Okay. Let's see what happens. Yeah, you see here it's no solution because, as I said earlier, some equations don't have solutions and some do. So the question now is, when will we expect to have solution and when we don't have a solution? Okay. So I wanted to take a step back and formalize this problem in a more structured way. Okay. And then I will show you the implementation details of this linear Diophantine, which I wrote. All right, let's get started with some high-level model first, a model of the equation. Suppose I say like this way, instead of all those constants that are hard-coded, I want to start from a more general way. Suppose I'm given an equation a times x plus b times y equal to c. And I wanted to find the solutions to this equation if they exist. Okay. And I'm going to show you an interesting theorem. Okay. Here a, b, c, x, y, z, x, y, c are all integers. They can be positive, negative, it doesn't matter. Okay. In the previous segment, we talked about how to find ax plus by equal to d using extended Euclidean algorithm. In this segment, I'm going to show to you solving a general equation like this. Okay. So if you are able to find a solution for this equation, say you found some numbers x and y which satisfy this property, what it means is that, let's say d is the GCD of a comma b, we can immediately conclude that d must divide c. Okay. If a solution exists to this equation 1, then d must divide c. What is d? D is the GCD between a and b. Okay, I'll prove this in a moment. We can also go backwards. Okay, if your GCD divides c, then there exists x and y that satisfies the equation number 1. Then solution exists, basically. Solution exists. All right, so let's take the forward direction first and then go to the reverse. Solution exists. Okay, so how do we go about this problem? Okay, let's assume that I'm going to go in this direction first now. Okay, let's assume solution exists, ax plus by equal to c. So that means you found x and found a y which satisfy this property number one. Okay, equation number one. I need to show d divides c. How do I do that? We do know d is GCD of a and b. That means d divides a. That's the meaning of GCD, and d divides b. Okay, that just comes from the definition of GCD we talked about earlier. If a number d divides a, d divides b, it also implies d divides any linear combination of a and b. That's another thing that you can easily prove. Okay, I leave that as a homework for you, but this is easy. If d divides a, d divides b, then you can be sure that d divides the linear combination of a and b. Okay, what is the meaning of ax plus by, which is nothing but c, because we assume that is true. So d divides c, okay, which is exactly what we need to prove. So we proved the forward direction. Now let's do the reverse direction, meaning if d divides c, solution exists. Okay, so let's assume d divides c. So what does that mean? It means we can write c as d times some number, I don't know, c1, right? That's the meaning of d divides c. Okay, now we do know that d means GCD of a and b. That means through the extended Euclidean algorithm, we can find some x and y such that a times x plus b times y is d. Okay, but remember, our goal is to find x and y to satisfy equation number one. We have almost gotten there, but on the right hand side we have a d instead of a c. So we need to somehow bring a c there, which means if you multiply this equation both sides by c1, well, what will we have? We have a c1x plus b c1y is equal to d times c1. Okay, what is d times c1? D times c1 is nothing but c. Therefore, we found out that a times c1x plus b times c1y is equal to c, which is the goal. Okay, the goal is to find some value. So we can take this as the solution. For example, we can take this as a solution. There are multiple solutions. I'll talk about it in a moment. So we can say the solution x1 is nothing but c1x. Okay, I'm going to use a slightly different notation here to avoid any confusion. We're given the equation 1. We do know d is equal to GCD of a and b. Therefore, we will be able to find, say, two numbers, x1 and y1, which satisfies this equation. I'll put x1 here, y1 here, x1, y1. Okay. So what it means is that now we can treat two solutions. We got two solutions. This is one solution for the x part. This is another y part. Okay, that's basically it. So essentially, we got something that is looking like equation number one structurally. They are no different, right? That's basically the point. Okay, so we were able to come up with the equations, solutions to the equation number one. Maybe we can treat this as x0 if you want to make it more clear. Solution for equation number one is c1x1 equation and another value y is c1y1. Okay, I will explain that. We know all of the values for this. Okay, we know c1 because c1 is nothing but just a quotient when you divide c by d, right? We can find d easily because of the Euclidean algorithm. So we know c1. You also know x1 and y1 because of extended Euclidean algorithm. So you found a solution to this equation. Okay, a solution. Okay, what about other solutions? Well, it's easy to see other solutions. For example, all you're going to do is, I'll generalize this, right? This is a solution. Okay, what are the other solutions? We can take x0. Okay, more solutions here. If x0, y0 is a solution to the equation 1, other solutions are x0, what can we do? Plus n is some integer, right? What are the other solutions can I write for you? You can use the division property now. We can just say the other solutions are b by d. Okay, that's another solution. And what about the y pair? Y0 minus n a by d. Okay, this pair of numbers, for different n, you get different solution. That's it. So this pair becomes another solution. When you put n equal to 0, you get x0, y0, which we know is a solution. When you put n equal to 1, you have x0 plus b by d. Okay, so let's go and put it here. So x0 plus b by d, we can check it quickly. Okay, let me show you how to do that. N is an integer, any integer. So that means there are multiple solutions. Interestingly, if there exists a solution to the equation number 1, there are multiple solutions. Otherwise, there are no solutions. Okay, because n belongs to an integer z. So why is this a solution? We can go and substitute this on equation 1, and we see both sides cancel out easy and get c on the right hand side. So take a multiplied with x0 plus n into b by d, right? So you have ax0 plus a b n by d, that's the meaning. And you have plus b y0 minus is useful because that's where you will cancel out the common terms, a by d. Okay, now if you add these two, the a times n by d, a times n b d, n by n b by d will cancel out with minus a times n b by d, which means you are left with ax0 plus by0, which you know is a solution because we found out that x0, y0 is a solution, which means this is nothing but c. All right, that's basically it. So we know how to solve a linear Diophantine equation, and we do know when a solution exists because we just proved it that if a solution exists, the GCD of a and b must divide the right hand side c. If the GCD divides right hand side c, we also know a solution must exist for the equation number 1. So we found an if and only if condition. So we do know when a solution exists and when it doesn't exist. So another important thing we know is that if a solution exists, there are multiple solutions. Just because all you have to do is just add n into b by d. D is a GCD of a and b. B is an integer. Therefore, this is going to be an integer, and this is going to be an integer. N is also integer. You keep changing n, you get new solutions for this problem. Okay, that's all. So in the next segment, I'm going to talk about how to make use of this to solve linear congruence. Okay, instead of equations, I'll have congruence. All right, thank you very much for your attention.